All right, welcome to the Explainer. Today, we're going to talk about something that's, well, it's everywhere. It's an invisible pulse that connects the color red, the music on your radio, and even the very data that makes up our digital world. It's a concept you've definitely heard of, but you might not realize just how deep it goes.
So to get us started, I've got a little puzzle for you. I want you to think about 3 things that seem totally, completely unrelated.
Okay, first up, the color red. You know, that deep, brilliant red of a stop sign, or a perfectly ripe strawberry. Just get that color in your head.
Next, think about radio waves. They're totally invisible, right? But they're carrying your favorite song through the air straight to your car. And last but not least, that low hum, you know the one I'm talking about, that you sometimes hear when you're near a wall outlet. So what on earth could a color, a radio broadcast, and the electricity in your house possibly have in common? Well, the answer is one single, really powerful idea.
All right, you ready for the answer? The one thing that connects all of those is frequency.
So what is frequency? Well, in the simplest terms, it's just how often something repeats over a certain amount of time. You know, like clapping your hands. If you clap once every single second, the frequency is 1 Hertz. That's it. That's the basic unit we use to measure the stuff.
And this is where it gets interesting, because frequency has this partner in crime, wavelength. And they're kind of like a turtle and a rabbit. A low-frequency wave is like the turtle. It's slow, its cycles are all spread out, which gives it a really long wavelength. But a high-frequency wave, that's the rabbit. It's super fast, with its cycles all packed tightly together, making for a super short wavelength.
Right. So the really crucial thing to get here is that they have this perfectly balanced inverse relationship. Because light travels at a constant speed, that's just a universal rule. If the wavelength gets shorter, the frequency has to speed up to compensate. And, it works the other way around too. One goes up, the other must go down. It's a perfect trade-off.
Okay, so that's the basic physics. But here's where it gets kind of mind-blowing. Let's look at how this one simple concept literally paints our entire reality, starting with something called the electromagnetic spectrum.
So check this out. This whole spectrum, everything from these long, kind of lazy radio waves all the way up to these super high-energy gamma rays, it's all just light. The only real difference is the frequency they're vibrating at. It's the same fundamental stuff, just with a different pulse. Kind of wild, right?
And because we figured this out, we can harness these different frequencies to do incredible things. We use low-frequency radio waves to send signals across the planet, and we use high-frequency X-rays to literally see the bones inside our own bodies. Each frequency gives us a totally different superpower.
Now, in that tiny, tiny little slice of the spectrum that we can actually see with our eyes, frequency is literally what color is. A slower frequency, boom, you see red. As it speeds up, we move all the way through the rainbow to violet. So color is just our brain's interpretation of frequency.
And what's really cool is that the exact same principle is true for sound. A low frequency, say 20 vibrations a second, well, that's that deep bass you can feel in your chest. Crank that way up to 20,000 vibrations a second, and you get a super sharp, high-pitched sound. It's all just frequency.
Okay, so we've seen it in nature. Now let's switch gears and see how this very same idea, frequency, is the backbone of the technology that powers our entire modern world.
Hey, remember that hum from the wall outlet we talked about at the beginning? Well, that is frequency in action. The electricity that powers pretty much everything you own isn't a steady stream. It's alternating current. It's flipping its direction back and forth either 50 or 60 times every single second, depending on what part of the world you're in. That's the hum.
Okay, but think about this. The world around us is, well, it's smooth, it's analog. The sound of a voice, for example, is a continuous wave. So how do we take that and turn it into digital ones and zeros? Well, we have to get clever, and surprise, surprise, frequency is the key.
The way we do it is through a process of measurement, or conversion. There are a couple of steps, but the one we really care about right now is called sampling. And sampling is all about frequency.
So what we're doing is basically taking a ton of snapshots of that smooth analog wave, really, really fast. We're measuring it at set intervals. And the speed at which we take those snapshots, the sampling frequency or sampling rate, is what determines how good our digital copy is going to be.
And it's not just guesswork. There's actually a golden rule for this, called the Nyquist theorem. And it's pretty simple. To perfectly capture and rebuild that original sound wave without losing any information, you have to sample at a frequency that's at least twice as high as the highest frequency in the sound itself. This is exactly why a music CD samples audio at 44,100 times per second.
Human hearing tops out around 20,000 hertz, so by sampling it more than double that, we make sure we capture everything.
All right, get ready for a bit of a plot twist. Because frequency isn't just about waves and electricity and digital audio. It turns out it's also one of the most powerful and fundamental tools we have for making sense of, well, data.
Okay, look at this screen. What you're seeing is just a raw data dump. These are the mileage ratings from an EPA test on 25 cars. And, it's just a mess of numbers, right? It's almost impossible to see any kind of pattern in that chaos.
But what happens if we apply the concept of frequency here? In statistics, frequency just means how often something happens. So instead of looking at the raw numbers, we just count. We count how many cars fall into different mileage buckets. And suddenly, a structure starts to appear. We can immediately see that most of the cars, 12 of them in fact, landed in that 36 to 39 miles per gallon range.
And then, when we take that frequency table and visualize it as a simple bar chart or a histogram, bam, the pattern just jumps right out at you. The chaos is gone. And in its place is this clear shape that tells us the story of the data instantly. It shows us exactly where the performance of most of these cars is clustered.
So what's the big takeaway from all of this? When you step back and look at it, frequency is this kind of universal language. It's the vibration that creates the light we see and the sound we hear. It's the oscillation that powers our homes. It's the sampling rate that builds our entire digital world. And it's the simple act of counting that lets us find patterns hidden in plain sight. It's the universe's way of describing repetition.
And that really makes you think, doesn't it? If this one simple idea, just counting how often things repeat, can connect so many different parts of our reality, what other incredible patterns are out there, all around us, just waiting for us to figure out what to count?